This is a video about voltaic or galvanic cells, also known as batteries. Voltaic cells use spontaneous oxidation reduction reactions to convert chemical energy into electrical energy. The most common application of voltaic cells is in batteries. So really important basic idea of how voltaic cells work. I've mentioned before about spontaneous reactions. That means that they occur naturally by themselves. You don't have to force them to happen. So these are all going to be spontaneous redox reactions, and they're going to be there to convert chemical energy into electrical energy. Those are the two identifying characteristics of voltaic cells.
Well, many of the wonderful things in our modern lives are based on one simple premise: putting a device between the two halves of just such a reaction, the half that donates electrons and the half that accepts them. By harnessing that energy, a lot of the coolest things you've done today, up to and including watching this episode of Crash Course Chemistry, has been made possible.
Okay. So a voltaic cell, if a redox reaction in an electrochemical cell happens spontaneously and produces electrical energy, it is considered a voltaic cell. The cations in solution are reduced when they gain electrons at the surface of the cathode, because remember the cathode is where reduction happens. They both start with a consonant, to become metal atoms.
Batteries. Now, if each of these half reactions occurred in contact with the other one, they'd just spontaneously go to equilibrium, releasing energy as a bunch of heat, which wouldn't be very helpful. So batteries are designed to harness that energy by isolating the half reactions from each other. This allows excess electrons to build up in the negative terminal, called the cathode, while an electron vacuum of sorts occurs in the positive terminal, the anode. Electrons can then cross from one half reaction to the other only when we connect the cathode and the anode of the battery via conductors, so the current can be used to do work, which I can do by licking this 9-volt battery. In these batteries...
Okay, so the half reaction for the cathode is the copper ions are going to be reduced to copper metal. And for the anode, the zinc metal is going to be oxidized to form zinc ions, and they're going to release 2 electrons. Electrons that are given up at the anode, because remember the anode is where oxidation occurs. Oxidation is losing electrons. So electrons are lost at the anode. They can pass along the external wire to the cathode where reduction occurs. The movement of electrons through the wire must be balanced by the movement of ions in solution. And that can happen through either, this example is a salt bridge. So you can either have a porous barrier where the anion can cross through the porous barrier, but the metal ions cannot, or you can use a salt bridge if you're completely separating the half cells. Anions move to the anode to replace the negative electrons that are moving away. So you have movement of electrons from the anode to the cathode, and then you have these negative ions. In this case, it's the chloride, because you've got, where did the chlorine come? Oh, because it's the salt bridge. So the salt bridge is made of potassium chloride. So you got potassium and chlorine here, and those ions, the chlorine ions, can move to the anode to replace the negative charge that's leaving. Because remember when we were balancing redox reactions, not only do you have to balance atoms, but you also have to balance charge. So if the anode is losing negative charge, you have to replace that negative charge, and that's what the salt bridge does. Cations are going to move to the cathode as positive charge is lost through reduction. So again, at the cathode, you have copper ions that are positively charged, which are being reduced to copper ions. So you're losing positive charge on the cathode side. So potassium ions from the salt bridge are going to move into this solution to balance the loss of positive charge. So you have negative ions going towards the anode, positive ions going towards the cathode. Dry cells, or batteries, are common sources of electrical energy. These are voltaic cells. The 3 most common types of batteries are the zinc carbon battery, the alkaline battery, and the mercury battery. So I'm going to go through those three types of batteries and basically like how they work. It's basically just a matter of using different metals and electrolyte solutions. So the first one is zinc carbon dry cell. This consists of a zinc container, which is the anode. So that's the outside shell of the battery. That's made of zinc, and that's the anode. So this is where oxidation is going to occur. It is filled with a moist paste of manganese dioxide, graphite, and ammonium chloride, which you see here. When the external circuit is closed, the zinc is oxidized at the negative electrode, which is the anode. So this is the half reaction. We have zinc being oxidized to zinc ion, so you lose electrons. Electrons move across a circuit and re-enter the cell through the carbon rod, which is the cathode, that's here. Okay, that's the positive terminal. The manganese dioxide that is in the electrolyte paste is reduced in the presence of water. So we have manganese dioxide in the presence of water is reduced to Mn2O3 and hydroxide. Okay, so the next type of battery is the alkaline battery. This does not have a carbon rod cathode. And this allows these batteries to be smaller. They use a paste of zinc metal and potassium hydroxide instead of a solid metal anode. So the half reaction at the anode is zinc plus hydroxide from the potassium hydroxide electrolyte. Zinc is going to be oxidized to form zinc hydroxide. The reduction half reaction, which occurs at the cathode, is the same as the zinc carbon dry cell, and that is the manganese dioxide in the presence of water is reduced to Mn2O3.
Let's start with the typical redox reaction that happens in this alkaline battery as an example. In here, elemental zinc is going to react with manganese dioxide, also known as manganese 4 oxide, to produce manganese 3 oxide and zinc oxide. When you break this down into half reactions, first you have elemental zinc with an oxidation number of 0 being oxidized to zinc 2 ion. At the same time, manganese 4 is being reduced to manganese 3. When we balance the half reactions, we see that 2 electrons are released during the oxidation of each zinc atom, and 1 electron is consumed by each manganese 4 atom. The water and hydroxide ions, by the way, come from a solution of potassium hydroxide, which is a basic or alkaline compound, which is why we call these things alkaline batteries. Now, if you just...
Okay, so the alkaline battery is the most common battery, like you saw him holding there, the AA, AAA, not like that. And the last one is the Mercury Battery. These are the really small round ones. These are the ones that you find in hearing aids and calculators. The anode half reaction is the same as in the alkaline dry cell. So you have zinc in the presence of potassium hydroxide is oxidized to zinc hydroxide. And the half reaction is using mercury. Mercury oxide is reduced to mercury, which is why it's called the Mercury Battery. So they're all basically the same thing. They basically, they are a completely self-contained electrochemical cell that has spontaneous redox reactions. And when you close the circuit, those spontaneous redox reactions occur spontaneously and produce chemical energy, which is then converted into electrical energy, which is what allows us to use them in electronic devices like calculators and hearing aids and etc. Now, something quite different is something called a fuel cell. This is a voltaic cell where the reactants are continuously supplied and the products are continuously removed. Unlike the regular battery, it could in principle work forever. They are very efficient and they have very low emissions. You can see from this diagram, you basically have hydrogen gas going in, and you have oxygen gas going in, and you've got potassium going to the right and hydroxide going to the left. and you basically only produce, I say basically a lot today, you're only producing water.
But how does the fuel cell work? A single PEM fuel cell is made up of 2 plates, 2 electrodes, and 2 thin layers of platinum-based catalyst, separated by a plastic membrane, which, when fed with the fuel, reacts electrochemically to create electricity. Hydrogen from an onboard storage tank and oxygen from air are fed through channels in the plates. Hydrogen flows on one side of the membrane, air on the other. The catalyst splits the hydrogen molecule into protons and electrons. The protons can pass through the membrane. The electrons cannot, and have to pass through an external circuit, creating useful electricity. On the oxygen side of the membrane, the protons and the electrons react with oxygen from the air in the presence of a second catalyst layer, generating water and heat. By stacking together single cells, like slices in a loaf of bread, you make a fuel cell stack to produce the required amount of power.
Corrosion is an electrochemical process that has a large economic impact. About 20% of all iron and steel produced is used to repair or replace corroded structures. Rust, which is hydrated iron 3 oxide, forms by the following reaction. We have iron in the presence of oxygen and water is going to yield iron 3 oxide hydrated, which is rust. The amount of hydration varies, which is why there's an X in front of H2O, and this affects the color of rust formed. The electrochemical reactions that occur during this process: at the anode, we have iron being oxidized to iron 2, and at the cathode, we have oxygen being reduced to hydroxide. The anode and cathode reactions, however, occur at different areas on the metal surface. The circuit is completed by the electronic flow through the metal. This acts like a wire in the electrochemical cell. So basically, the anode and the cathode are completely different parts on the metal. And because of the characteristic of metal being that they have delocalized electrons that can flow, that automatically acts as the wire in the electrochemical cell. And water serves as a salt bridge, which is why water is required in order for rust to form. So for corrosion to occur, water and oxygen must be present. So this is what I mean when I say that the anode and cathode are at different areas on the metal. So you'll have parts of the metal where the metal is corroded away, and then other parts of the metal where the rust builds up. It doesn't just build up on top of where it's eroded. So when iron is exposed to water and oxygen, the metal at the anode here is oxidized to iron 2 atoms, which you see here. Not very clear, but you see it anyway. The electrons that are released are going to travel along the metal to the cathode. The iron 2 ions will travel along the moisture, which is here, to the cathode as well. And at the cathode, the iron 2 ions are further oxidized to iron 3 ions. So how do we prevent this from happening? We can coat the steel with zinc. This is called galvanizing. Remember when I said at the beginning that voltaic cells are also called galvanic cells? Zinc is more easily oxidized than iron. That goes back to the oxidizing and reducing agent video that I talked about, and that the table that you have in your book about which metals are more likely oxidized or which ones are more likely reduced. So zinc is more easily oxidized than iron. So if we coat our steel, which has iron in it, steel is an alloy of iron, which means that it's iron mixed with other elements. I do believe carbon is part of it, but I don't remember everything that makes up steel. But if we coat it with zinc, that means that the zinc is oxidized before the iron starts to oxidize and before rust is formed, and this is called cathodic protection. So the more easily oxidized metal we call the sacrificial anode, which is in this case the zinc.